Okay, so welcome to this next talk. This is Dr. Armin Tavakoli. And Armin Tavakoli is recently joined as an assistant professor at Lund University in Sweden. And he did his PhD from University of Geneva under the supervision of Dr. Nicholas Brunner and Professor Gissin. And he did actually, we know him, I mean, he's very known to India, I mean, in the community, because we, all of us actually follow his works. And his PhD thesis that is published in 2020, and that was the best prize, thesis prize. And also after doing the PhD, he moved to for a postdoctoral position at Vienna, and he received the Entropy 2020 Young Investigator Award. And his works includes the topics that is quantum information theory, and he publishes many works in quantum foundations, and he works in quantum thermodynamics and the non-classical feature of quantum communications and non-locality in quantum networks. Today, he will be talking about the entanglement in quantum communication. So with this, I would like to invite Dr. Tavakoli to give his lecture.
Thank you very much for this very kind introduction. I'm very happy to be here and get the opportunity to deliver this introductory talk to you all. Can you confirm that you can see my screen?
Yes, you can see your screen. Yes.
Very good. Okay, so today I'm going to talk to you a bit about entanglement in quantum communication, which is a quite recent topic that we have been pursuing fairly intensely in the last couple of years. So I want to share with you some of my excitement about this. What this does is that it goes back to some very elementary and quite old problems in quantum information science. Let's take a look at the broad sketch. Here on the left, you see the typical scenario in which we usually study entanglement. You have a source of two particles. It emits one to the left, one to the right. Then the parties perform some measurements and get some output. And then we typically study those correlations to try to learn whatever it is we are interested in. In this scenario, we have entanglement, but no communication. Many times, the fact that we don't have communication is what makes the scenario interesting. For example, no signaling in Bell non-locality. On the right, instead, you see the typical scenario for studying quantum communication. A sender here on the left takes some classical data, creates some quantum state, sends it over a channel. The receiver receives it, performs some measurements that they select, and get some outcome. And in the end, we try to see what the receiver can learn about the input of the sender once they perform the measurement on the state. In this quantum communication scenario, we of course have a quantum channel connecting the parties, and we typically have no entanglement. These quantum communication scenarios are very well studied, and they have been studied for at least 15 years quite intensely. Here, you can see that you can think of them in a slightly more formalized picture. So I will call the sender Alice on the left and the receiver Bob on the right. And the classical data that Alice selects, that is the data set with which you encode the state, I call it X. The choice of measurement, which tells you what sort of property of X that the decoder wants to learn, Bob, I call Y. And the result of that measurement is called B. So the typical scenario is that you allow Alice and Bob to perform arbitrary operations, but you limit the amount of information that Alice can send to Bob. This can be done in many ways, but a traditional way is to limit the alphabet of the message. So you can have a bit, 0 or 1, but not 2. In a quantum case, that translates into a qubit, that is a two-level system. This is mainly justified by Hall-Level's theorem, which tells you that if you substitute a bit for a qubit, you cannot send more symbols over the quantum channel as compared to the classical one. Many times, simply because it's a very natural resource, we also allow Alice and Bob to share classical randomness, so a string of correlated data. In practice, we can think of this as them buying the same newspaper in their different labs and coordinating according to the letter frequencies. So a very basic question, which people have addressed since a long time, is what are the correlations, so the probability of getting outcome B when the data is X and the question is Y, between the sender and the receiver, if you have a classical correlation over the quantum channel. In fact, a whole lot of stuff is known about this, and I just highlight a few different things. One important thing is that there are many natural communication tasks where using a quantum system instead of a classical one gives you a communication advantage. You can simply perform the task better. Another example of this is quantum key distribution. You can use the quantum channel without making any assumptions on the devices of Alice and Bob apart from the dimension of their system to distribute a quantum key between Alice and Bob. A similar example is a quantum random number generator. You can use these type of communication scenarios to ensure that not only Alice, but also not an eavesdropper, cannot guess what is the outcome of Bob unless they can somehow work their way around the assumption of a dimension limit. But this is often called a semi-device independent approach for key distribution and random numbers. Another interesting thing is that these communication scenarios, they can serve as a platform that you can use to certify and benchmark the quality of your quantum devices. This is often called self-testing and certification. So for example, you go into your lab, you send a qubit over the channel, and you perform some measurements. And once you recover the data, you can deduce something about what your measurement device and the sender device, state preparations, are actually doing. Again, without making significant assumptions apart from the dimension. A complementary concept to this, which had a lot of traction about a decade ago, was called device-independent dimension witnessing, where you again assume that over the channel, I have a system with an unknown dimension, and only by inspecting the data that I receive once I perform my measurements, I say something about what is the dimension of the physical system. So that's a little overview of the many things one can use these communication scenarios for. But what we really want to do, which is the main point of this talk, is to add entanglement to the system. So now, instead of Alice and Bob being connected through a shared source of classical randomness, we are going to substitute it by a source of quantum randomness, that is an entangled state. Now, Alice and Bob get one share of the entangled state each. Alice can manipulate it and send a limited dimensional system over the channel, and then Bob will receive two pieces, one from the source and one from the channel. And these two pieces can be measured jointly to create the outcome. So the basic question that we want to explore is what is possible and what is not possible when quantum devices are now quantumly correlated. What is the role of entanglement in quantum communication? At this point, you might think this sounds awfully similar to the quite famous dense coding protocol. And you're very right in saying that. Dense coding is very much a special case, the most famous special case of this type of scenario. I'll quickly remind you, or for those of you who haven't seen it, briefly summarize what this protocol does. If you don't have entanglement, so business as usual, you can take an input state, code it into a qubit, and try to send whatever your input was to the receiver. So the state goes over the channel, measurement is performed, a guess is constructed. What is known is that if you send the qubit, you cannot transmit more than two symbols over the channel. But if you do dense coding, you can share an EPR pair, so a maximally entangled 2-qubit state between the sender and receiver, and suddenly, only by sending a qubit over the channel, you can send 4 symbols, so 2 bits of communication. What happens is that the sender is doing a unitary rotation on one share of the state, then sends over the particle, and now you have an element of the Bell basis that you can then project onto the Bell basis and decode the actual symbol. What we want to do here is to go beyond dense coding, and very much the point of this talk is to show you that entanglement in quantum communication is quite a lot more than just the quite spectacular dense coding protocol. And to try to tell you why I think this is the case, let's start with the simplest scenario. That is when you just send a 2-level system, a qubit, over the channel assisted by entanglement. Dense coding, as we have just seen, uses an Einstein-Podolsky-Rosen pair to send 2 classical bits over the channel. It's essentially equivalent to a classical protocol, but with twice the communication. But it's natural to imagine that you can be a bit more sophisticated than that. You could do something that I like to call generalized dense coding. So again, you share a maximally entangled state, the EPR pair, but now you can perform arbitrary unitary transformations of the qubit before sending it over the channel, and then making arbitrary measurements of the 2 qubits now collected at Bob's site. This seems to be a very natural approach to do these entanglement-assisted communication problems. But in principle, we can imagine something more general. This would be that we have a very high dimensional entangled state here, but when it comes to Alice, it would somehow have to be compressed into a qubit. It has to be decohered globally. And then once it arrives at Bob, you will get a qubit over the channel and a piece of a high dimensional state from the source. And this state will be noisy and its entanglement will be reduced because of the squeezing or compression operation of Alice. So you could imagine, well, this is probably not a good idea, but we will return to it. It's certainly a possible thing, and it turns out that it's quite an interesting one. But before we get there, let's talk about generalized dense coding. Generalized dense coding admits a rather elegant isomorphism with real quantum mechanics. And I want to quickly outline how you get there from here. So imagine you have a bunch of states, psi x. If you want to characterize them up to a global rotation, all you need is to look at the Gram matrix. So it's the matrix of all the overlaps between these states. Now the thing is that any qubit unitary, you can always write it as some Pauli operator, sigma, and some linear combination of them. Now there are 4 Pauli operators, x, y, z, and identity. So this combination factor here is just a vector whose length is 1 to preserve the unitarity. Now, the encoded state in our entanglement-assisted problem is to give you an EPR pair, maximally entangled state. Alice does some unitary, which is now this form for a qubit. And we can then just put this straight in here and calculate the Gram matrix. Well, a straightforward calculation. You take the maximum entangled state, sandwich it after the transformation. This reduction is just a maximally mixed state, so you get the overlap of the 2 unitaries. And then you just take this formula and plug it in here. And you'll see that what you have is an overlap between 2 Bloch vectors, so 4-dimensional vectors here, and some phase. But we can always remove this phase simply by substituting the original state with a phase shift, which can always be done locally. So in fact, we can drop this phase factor in the end and just see the Gram matrix as an inner product between 2 real vectors of dimension 4. Why this matters is that this shows that generalized dense coding is in fact equivalent to an entanglement unassisted communication of a real QQT. So just to show you what this result really means, if you are here with a maximally entangled state and you do some arbitrary unitaries and arbitrary measurements with a qubit over the channel, the correlations you can create are exactly identical to those you can create in a normal without entanglement scenario, where you send a 4-dimensional systems that only has support on a real Hilbert space. There is a connection between real quantum mechanics and entanglement assist protocols. So now we know generalized dense coding is isomorphic to real QQTs, and real QQTs are essentially systems that we have worked with before. You don't need entanglement for these. They are good old quantum communication without entanglement. We can recycle the tools known since many years to analyze them. So now we have to go back to those higher dimensional entangled states, but that we then have to squeeze through the channel. And we asked, is this even a good idea to try to decohere entanglement to improve communication? The rather striking answer is that the answer is actually positive. By having high dimensional entanglement, compressing and decohering it through a qubit channel, and measuring a noisy, dimensionally asymmetric entangled state here, you can perform tasks that generalized dense coding never can do. And I will very briefly sketch you an example of how this can work out. The task is twofold. One part is a so-called random access code. This means that Alice has 2 bits, 0001, 10, and 11, and Bob has 2 questions, 1 or 2. The job is to recover bit number 1 when y is equal to 1, and bit number 2 when y is equal to 2. So the answer is simply to output that right bit. The better you can do this, the more likelihood of succeeding, the better you perform the task. But on top of that, there is an extra constraint. Alice has a 5th input, and Bob has a 3rd question. And when Bob does the 3rd question, he's asking, is Alice's input equal to the 5th one, or is it one of the other 4? It's a task of quantum state discrimination. What we ask is that you do the random access code as good as possible while achieving a perfect quantum state discrimination. So we can analyze this problem. First, for normal dense coding type protocols, how often can you provide a success in the random access code task? Well, we know that dense coding is essentially a classical problem with twice the channel capacity. So we can solve this by established classical methods, and we get a success rate. Generalized dense coding, we know, is equivalent to standard quantum communication with real four-dimensional systems. So we can recycle old methods known for that. And then we get a limit which is notably larger than the dense coding limit. You can do better by doing a more sophisticated protocol than standard dense coding. But the real point is that if you use two pairs on a maximally entangled state, so effectively a four-dimensional maximally entangled system, bin one of the qubits on Alice's side in a compression channel and send the other one to Bob, you can in fact improve on the best conceivable rate for any generalized dense coding protocol. Decoherence of a higher dimensional entangled state, noisy entanglement, and asymmetric measurement dimensions for Bob is in fact a resource entanglement assisted quantum communication. So now we know that we cannot get away with the simple intuition that the entanglement dimension should be the same as that of the channel. So is there a sufficient entanglement dimension? Is it 100 or 1,000 or maybe infinite? We don't know. In fact, this is one of the very nice open problems here. What we decided that we need to do is to understand how to characterize the set of all possible correlations in this scenario for any number of inputs, outputs, inputs on Bob and outputs on Bob, both in the case where the dimension, the system over the channel is classical and when it's quantum. But importantly, the amount of entanglement they share can be absolutely anything. It's not limited by the dimension, it's countably unbounded. So we are looking for methods to characterize the ultimate limits of entanglement-assisted quantum communication. Here is a little sketch of how we want to do that. So what you're seeing here is the space of the correlations. So the probability of getting outcome B when the data is X and the question is Y. Here you see the classical case, meaning you have unlimited entanglement, but classical messages. And here, unlimited entanglement, but quantum messages. What we do in our work is that we provide methods to first bound each of these sets from the inside. These are the purple lines. And then we find, more importantly, methods to bound them from the outside. These are the orange lines. So if you're given a correlation, which is outside the blue set, you can use our relaxations, the orange line, to test whether it actually belongs to the quantum set, whether there exists some conceivable quantum protocol that could somehow create this prediction. The way we do this is through semi-definite programming relaxations. And in fact, we build two entirely different methodologies for doing this. The first method, which might be more familiar to you, is based on the rather well-known Navasquez-Pironio-Assin hierarchy. But there is an immediate catch, and it's that the NPA hierarchy is originally based for Bell non-locality. And here we are not doing Bell non-locality, we have a communication line. But it turns out that, at least in the simplest classical case, which means the message over the channel is classical, you can connect Bell non-locality to these types of problems. To see how you do that, so imagine you have this state, phi, shared. Alice has now to convert that share into a classical message. This means performing a measurement with D possible outcomes, where D is the dimension of the channel. So she chooses measurement X, gets outcome M for the message, and then relays it to Bob. This means that the state on average received by Bob is this thing here. So the state is there, Bob does no action on his side, Alice does her measurement. Then we forget about Alice as part of the state, and she sends the outcome, over the channel. And then this has to be averaged out because each of the messages are possible to receive by Bob. Now, once Bob receives this state, smart thing to do is to first read the classical register, M. This he can do deterministically because it's a classical message. And then once he has learned M, he can measure the remaining part of the register on the right side. So the correlations would be this. You read the message, adapt your measurement to that, and then perform a measurement on the residual part of the state. What you see here is Born's rule, essentially, for a Bell problem, except that the outcome of Alice now appears as an input on Bob as well. But this type of problems can be addressed by the type of NPA relaxation methods. So this is what we do. In the quantum case, where you have a quantum channel, this reasoning doesn't work. You have to do a bit more sophisticated connection to the NPA, but the spirit is the same. You can reduce entanglement-assisted problems to a non-commuting polynomial optimization problem. But what we also do is to give a completely different methods for achieving the exact same thing. So another way of doing semi-definite relaxations for entanglement-assisted quantum correlations, but without resorting to NPA connections. The way we do this is to go through the concept of informational restrictions, which is something that was developed back in this work. The idea is extremely intuitive. Imagine for a moment that you have Alice here with some data X, and using the entanglement and the d-dimensional classical and quantum channel or quantum channel, she will send a message to Bob, and Bob wants to learn her symbol. So he wants the output be equal to the input of Alice's data. So this is essentially state discrimination or information recovery, however you want to call it. Question is, how well could Alice and Bob ever perform this protocol using arbitrary measurements, encodings, and states, only limited by the dimension of the classical or quantum channel? This we can in fact translate into an information quantity. It's known that this type of operationalism, so state discrimination, is one-to-one with an information quantity known as the minentropic accessible information. What you see here is the definition of that. You can see that this definition is actually very similar to the normal information between two parties. But here we are using minentropies instead of Shannon entropies. The reason that we use minentropies is because it admits this operational connection to state discrimination. So what it tells you is that the information gain about the variable X, once you have access to Bob's outcome, is essentially the same up to some logarithms of the probability of state discrimination, which is what we have written here. So how well can you do state discrimination with entanglement-assisted quantum communication? The main observation, which I will not prove, but it's quite intuitive, is that if you have a classical channel or a quantum channel, the amount of information you can send is exactly log d bits in the classical case and twice as much in the quantum case. Dense coding is achieving exactly that. It can be viewed as a one-shot version of dense coding and the whole-level theorem, respectively. Why do we care about this? This is the reason. We want to use information relaxations to address the problem we care about, namely bounding entanglement-assisted correlations in quantum mechanics. So here is the problem we care about: entanglement and a quantum channel or a classical channel. What we do now, we relax it to an informationally restricted scenario that doesn't feature any entanglement, but it has a limit on the amount of information that can go over an otherwise uncharacterized channel. We know that this scenario is strictly stronger than the one we are interested in. But then, in our original work for informationally restricted correlations, we developed rather efficient semi-definite relaxation hierarchies for bounding all the predictions of quantum mechanics for these types of systems. So what we can do is to recycle those results and get efficient computation on the scenario of interest. If I put these two methods side by side, you will see why I care about having two different ones. Here you have the NPA connections, and here you have the information-based methods. The advantage of the NPA type methods is that they converge. If you do a sufficiently large and complicated relaxation, you will eventually converge to the actual quantum set and get a necessary and sufficient condition for whether a behavior is quantum or not. In the information-based scenario, you cannot do this, and the reason is the step from the scenario of interest to the information step. This is not tight, but it's remarkably accurate. In our tests, roughly 98 to 99% success or accuracy probability is what we have been seeing. And in many cases, we have seen that it is entirely tight, that is, no relaxation is happening at all. But the advantage is that NPA methods are exact and information-based ones are not guaranteed to be that in general. However, the information-based ones have a remarkable practical limitation. That you can see in the size of the semi-definite program you have to solve to obtain a bound. The number of operators that you need to deal with in NPA scales linearly in the dimension if your system is classical, so the channel is classical, and quadratically in the dimension if the state over the channel is quantum. In the information-based case, is completely independent of the dimension in both the classical and quantum case. It means that you need to deal with much smaller semi-definite relaxations, and therefore you can compute much more sophisticated relaxations. One is conceptually nice, the other one is practically handy. So let's move on now from this into some more conceptual ideas. The traditional way of dealing with entanglement-assisted communication over a classical channel is depicted here on the left. The idea is that you can use Bell's theorem to propel communication beyond classical limits. This idea is almost 25 years old now. The idea is depicted here. So you take a state, you perform some inputs and outputs on the sender and the receiver, and then you check that you have violated a cleverly chosen Bell inequality. Then you send the outcome of Alice over the channel, and you use the outcome of Bob to classically post-process the final answer. So it's a two-step process. First, violate the Bell inequality, and then do a round of classical communication, and you will many times find that you can beat the limits of any protocol where you didn't first do the Bell round, so if you didn't have access to entanglement. These types of conventional protocols, I decide to call them non-adaptive. By this, I really mean that Bob does not adapt his settings to the message of Alice. There is really first one round where you check for Bell non-locality, and then you communicate. So really, there is no difference between non-locality and a quantum communication advantage over a classical channel. But the thing is that you could imagine that protocols could be more sophisticated than this and not rely immediately on Bell's theorem. Those ones I call adaptive. What happens here is that Alice receives the state, takes the input X, does a measurement A, gets an outcome N. That one goes over the channel. Now, what Bob does is to wait. So he receives his particle from the quantum state, he keeps it, he waits until the message arrives, and once the message arrives, he changes the way he is intending to measure the state, and then gets an outcome B. He's adapting in real time to the messages of Alice. So you're no longer dealing with Bell's theorem, it's actually a Bell theorem with signaling. What we can find is that these adaptive advantages can be rather significant. There are actually tasks where waiting for the message can do you better than not doing so by sticking to the traditional methods. You can see this again in the random access code that we discussed before. Remember, Alice has 2 bits, Bob has 2 questions, and the task is to learn either the first bit or the second bit. If you answer correctly, you win. You can see that if you just have 1 bit of communication over the channel, then it turns out that having a maximally entangled state here, violating CHSH between Alice and Bob, and then doing a round of classical communication gets you an optimal winning probability, roughly 85%. Using adaptive measurements can in no way improve this, and we showed the methods for how to deal with both adaptive and non-adaptive settings in this paper. The critical thing here is that somehow, even though adaptive strategies are more powerful, they cannot be used to enhance the task. But the funny thing is that if you now scale up and allow for 3-level communication, so you can send 3 symbols over the classical channel for the exact same problem, then the situation changes. One can prove that non-adaptive protocols, so Bell non-locality plus classical communication, are limited by a certain success rate, and that there exist adaptive protocols that can outdo this success rate. What is more nice is that non-adaptive protocols, as compared to adaptive ones, can be used to simulate very natural classes of entanglement unassisted quantum correlations. What we can show is that we look at the simplest possible standard communication scenario, no entanglement involved. Alice takes a data X, creates a qubit state, sends it over the channel, and then Bob can do arbitrary projective measurements of this. Similarly, there is a more general case where Bob can do arbitrary quantum measurements. So this can be not only projective, but also non-projective. Things like SIC POVMs are, for example, allowed here. This is the most general qubit communication protocol, and this is the standard one restricted to projective measurements. What we can show is that there is a very simple way of simulating both of these classes using entanglement and only classical communication. So for example, when your measurements are projected, we can prove that there exists a way where you use only a single EPR pair and one bit of communication, such that this correlations that created here simulate the projected measurements here. This is in fact a 20-year-old result shown in I think by Armin Tavakoli. And then what we can show here is that if and only if these measurements are non-adaptive, you can simulate the projected measurements. If you allow for adaptive entanglement assisted protocols, you can then simulate the general measurements, the POVMs. So if you decide to not adapt your systems, your simulation power is limited to a more natural but subclass of the total set of quantum communication systems, whereas adaptive measurements are both necessary and sufficient to simulate the whole set of POVMs, non-projective measurements. Now, that's for classical communication, where you can see that adaptive strategies are both more powerful and have natural simulation abilities. But what about quantum communication? What happens when the channel is quantum? Well, we know that adaptive measurements with quantum systems are much more sophisticated because they can be entangled. We can jointly measure both the message and the share of the system, and they are influencing each other all the time. But the problem is that these type of dense coding style entangled measurements are very challenging in practice. As a simple example, just take dense coding. Dense coding was discovered in 1992, but there is still not a single experiment that comes really close to the channel capacity limit of 2 bits. And the reason for that is that making an optical 2-qubit deterministic Bell state measurement is an exceptional challenge. You cannot do it with linear optics unless you use extra photons or resort to nonlinear optics. So if you want to somehow move away from the purely conceptual part to also become practically relevant, it's very much important to see if very simple measurements can be used to harvest in principle, powerful predictions that entanglement-assisted quantum communication makes possible. And this is what we have been exploring in very recent times. Can we get away from the entangled measurements and still keep most of the advantages? So we are interested in the power of simple measurements. What I mean by this is ideally measurements that don't require any entanglement at all. So for example, once Bob receives the qubit coming over the channel and the share coming from the entangled system, then ideally he should be able to measure the qubit and the entangled share separately and only classically post-process that outcome. Why is this good? Because single photon measurements are extremely much easier than entangled ones. The problem is that, for example, if you look at dense coding, it's well known to be completely impossible to have any classical advantage if you don't use an entangled measurement. So this seems to suggest that one is kind of in trouble. If you want to use simple resources, you lose all your advantages. But what we find is that this is not true if you go beyond dense coding and consider more sophisticated scenarios. Here is again a random access code. The only difference with the previous one is that Alice now has 3 bits instead of just 2, x1, x2, and x3, each one 0 or 1. Bob asks for the value of x1, x2, or x3, and if he guesses it right, he wins the game. What we will do is to permit an EPR pair and a qubit, so generalized dense coding. You do a unitary on Alice, Bob receives 2 qubits in the end and has to project them jointly. This is the astonishing thing. There is a protocol for this task in which Bob only measures product observables, specifically these ones. So both the channel qubit and the entanglement qubit are projected onto sigma z, then onto some simple reorientation in the block sphere, but all of them completely separable. What we can find is that the protocol that uses these very simple measurements not only outperforms the classical limit, not only outperforms the limit of using twice as much classical communication, that is using dense coding, but it is in fact the optimal protocol allowed in quantum mechanics. What that means is if we were to use some very complicated entangled measurement, we could not do better than the protocol using only product measurements. Simple measurements can, for natural tasks, sometimes be remarkably powerful. What this allowed us to do was to actually perform a rather simple experiment where we could harvest all the advantages of entanglement-assisted quantum communication using only beam splitters and phase shifts, because we no longer need to perform the complicated measurements. This is still restricted to dimension 2. To get the really spectacular advantages we expect, we have to go to high dimensions where any hope of a deterministic Bell measurement is essentially gone. But this shows you that in principle, separable measurements are powerful. The drawback here is that if you want to achieve a quantum advantage using these simple measurements, you cannot use very noisy entangled states. So as soon as you put a noise over a substantial threshold, then all the advantages over dense coding or classical systems simply go away. So the next step for us, which was the most recent work in this direction, was to show you that you can keep the cake and eat it at the same time. That is, you can have product measurements and at the same time have very noisy entangled systems that allow you to beat the classical limit. So now you're robust both to noise and can do it with very simple experimental setups. The way we show this is through a secret sharing protocol. Here you have Bob and Charlie and Alice. Alice wants to share a secret, A, with B and C. This secret should be shared in such a way that Bob and Charlie cannot access it alone. They have to collaborate to learn its value. So it's a bit like the movie sequence where the two people have to twist the key at the same time to unleash some sort of weapon. To learn any information on A, you have to collaborate. Now, to our assistants, we have a shared entangled state, rho, which first goes to B and C, and then a qubit is sent from B to A and from C to A. Here, we let Alice have a binary measurement called Z. The idea is that if Alice chooses Z equal to 0, then the secret is shared between X0 and Y0, so the 2 bits. If Z is 1, the secret is shared between X1 and Y1. To ensure that you have to collaborate to reconstruct it, our winning condition, or secret sharing condition, is that the secret is equal to the XOR of the 2 pieces of information individually held by Bob and Charlie. Now, here you can do a simple protocol to get an optimal secret sharing rate, so to ensure that this condition is always true, using only product measurements. The way you do it is to prepare a maximally entangled state here, do the Pauli rotations here and here, so the 4 Paulis corresponding to the 4-bit values. And once you receive the system here, instead of doing a Bell measurement, you simply project onto these coarse-grained variants of the Bell measurement, which are product measurements. You get a unit success probability. Now the question is, what happens if you have very noisy systems? So what we look at is states of this type. You have a partially entangled state here, tunable with some angle theta. And on top of that, we mix it with white noise. So here I is the identity, and you can choose the visibility range. So what we can find is that you can choose a value of theta, which is quite small, so weakly entangled, and a value of V, which is also quite small, so very noisy, such that this state becomes unsteerable. That is, it's not only Bell local, you cannot even steer it. It has no spooky action at distance. And nevertheless, although being so noisy and so weakly entangled, you can still use it to get an advantage in secret sharing using only these very simple measurements. So what that shows us is that somehow the very easy experiments based on product measurements, they have a hope of surviving even in very extreme noisy conditions. So the natural next step is to try to go to high dimensional systems, but there we still have a few results, and hopefully that will change soon. So I would like to wrap this little exploration up by concluding some elementary things that I hope I have been able to convey. The first one is that entanglement in a one-shot communication is a largely unexplored topic. What I mean by one-shot is that we are not working in the channel capacity regime, where we have infinitely many users of a channel, all of these infinite shares measured collectively, and vanishing errors in the limit of many copies. Here we have the operational situation, where you just have one user of the channel, like in a Bell non-locality problem. This topic is quite unexplored, and I think there is a lot of nice things still to be done here. Moreover, we can see that it really goes qualitatively and quantitatively beyond the dense coding protocol. Quantitatively, because we can easily find more methods that go far beyond the limits of what the dense coding protocol can do as soon as you move into tasks that are not only about sending and receiving a message. We saw this already for generalized dense coding, but more astonishingly also for these high-dimensional systems that have to be compressed through a channel, but are still able to beat anything resembling a dense coding protocol. We can also see that this happens qualitatively. Higher dimensional entanglement is useful. In dense coding, it's not. We can see that product measurements become very powerful, but in dense coding, they are completely useless. Entanglement-assisted one-shot communication can do quite a bit beyond its most famous example. And finally, I really want to emphasize the power of simple quantum measurements, and that this really could be an avenue to very efficient real-life protocols that are both experimentally feasible, viable in real life, but at the same time harvest all the potential of the strongest communication resource that we have, namely the combination of entanglement and quantum communication. So with that, I'd like to thank you for your attention, and hope you have any questions that I might be able to answer.
Thank you, Dr. Tavakoli, for the beautiful talk. And we are now open for 2 questions and comments.
Lagda, can I ask a question?
Yes, sure. Go ahead.
Armin, thanks for this nice talk. Yeah, so I have one question. Let's say we consider Px given B correlation. Px.
Sorry, can you say again what you want to consider?
Px given B means X is the input at Alice end and B is the output on Bob's end.
All right.
No Y is there, or at Bob's end, no Y is there.
Okay, no input.
Okay, so now I am asking this question. Let's Alice and Bob has unlimited shared randomness. One EBIT of entanglement and 1 qubit.
Okay.
So now we let's say we characterize the set of all correlation P B given X, P B given X, with the resources unlimited shared randomness, 1 EBIT and 1 qubit. Now I say instead of 1 EBIT, if we give 2 EBIT, will they generate a larger set of correlation in this P X given B given X scenario?
Yes, this is a very nice question. In fact, it's so nice that somebody has answered it already, and it's not me. There is a paper by Carlos Vieira and co-authors from 2022, where they show you that there exist correlations that does exactly what you asked for. In particular, what this uses is this result from Frenkel and Weiner. So what Frenkel and Weiner show is that if you have no input on Bob and no entanglement, there is no quantum over classical advantage in any dimension.
Exactly.
So now, if you have no input on Bob, but have entanglement, then, but entanglement of dimension 2, then you're effectively preparing a 4-level system here, which we know is a real QQT because of our isomorphism. So a real QQT can never beat a classical 4-level system because of Frenkel and Weiner. But if you have 2 EBITs, then this isomorphism with real QQTs breaks down, and you have this noisy high-dimensional thing on this side.
Yes.
And that they could prove indeed can achieve a classical an advantage of a classical system, and therefore also over the quantum system.
They explicitly give some task or something.
Exactly, they do that.
Understand.
It's a paper. It's certainly on the archive. Carlos Vieira and co-authors.
Understand. Okay. Thanks. Yeah. And once again, thanks for your nice talk.
Thank you. I'm happy you liked it.
Is there any more question? Okay, I have a question. That is the scenario you discussed about the product measurement and dense coding protocols. Can you go to this slide? Yeah, the scenario you described here, you have only 3 inputs for Alice and the 3 input for Bob. Can it be extended? I mean, is it for the only for the 3 input scenario?
So if you can extend it to more bits.
Yeah, more bits, yes.
I don't know, frankly. So this construction here was quite an accident. So we found it by coincidence, and we don't know why it's so good. So it's optimal for all quantum protocols. We don't have an intuitive understanding of it.
Yeah, go ahead.
Yeah, so since we don't have this intuitive understanding of why it works, we can only prove that it does work. We don't know how to extend it. It would be very nice if we could find a way.
Okay. I can see that is the U1, E2, E3 defined because in the second qubit you have only the kind of external POV measurements, right? So yeah, maybe I mean if you extend the external POVMs for higher dimensions, is there any possibility? Do you think?
Yeah. So to go to higher dimensions, this is something that we are pushing for now. So because we know that in high dimension, entangled measurements not only are difficult, they're essentially impossible for practical purposes. But product measurements are possible. So now we are trying to push for very high dimensional systems where we can detect large entangled systems by using very simple measurements. But also there, it's quite complicated. If we can do it right now for simple protocols, but I mean, nice constructions of these tasks are not easy, and I think it's really lacking in the literature. It's about time to find a solution.
Thank you. We have time, so you have more questions.
Can I ask a question?
Sure, go ahead.
Thank you for your talk. In your slide, I see a lot of optical elements. So first question is, do you consider also vacuum noise?
So so what's happening here is that we're doing polarization encoded entangled systems in 2 photons. So it's not a continuous variable system. The only reason, in fact, that I put these optical elements is to show you that the measurement is a very simple procedure. So you create the 2 photon entanglement here, couple it into the sender on one side. This is just a sequence of wave plate and phase corrections to encode the unitary. And then here in this box is the measurement. So what you see is that what's happening is that you're measuring 1 photon here and 1 photon here completely independently. And that is really the point I want to convey with this. So the vacuum fluctuations are essentially just a noise source in this experiment, but they are very tiny.
Mm-hmm. So BBO crystals you are using for creation of 2 orthogonally polarized photons, right?
Exactly.
Okay. Thank you.
So I think that we don't have more questions. If not, so let us thank Dr. Tavakoli once again for his beautiful and nice talk.